Good evening, everyone. My name is Rajat Bonik. I am from IIT ISM Dhanbad. I am also a PMR research scholar at IIT ISM Dhanbad. And I am in improvement. Class week 10, and only two more weeks are left of this course. And I am one of the TA of Professor Dilip Kumar Baddu sir, who is conducted this course on NPTL. So let's start our today's discussion. In our today's discussion, we try to cover these 10 week all lectures, and then, if time permits, we will discuss the previous year assignment problems and try to solve some question also. So let's start our session. I am sharing my PPT, so please wait. And one or two points is that if I am disconnected or my audio or video is not clear, please uh, please tell me in between this meeting. Uh, if I am disconnected from internet, please don't worry. I please stay on the line. I will join in few minutes, so don't worry about this. And also, this video is recorded and it will be shared to everyone through NPTEL team in my YouTube channel. And also, whatever I am discussing in this today's lectures or materials, it will be shared to everyone in Google Drive with, by NPTEL team. So don't worry about that. So let's start our today's class. So I am sharing my screen, PPT. Please wait. I think my screen is visible to everyone. My PPT will be visible to everyone. So let's start our. Oh, thank you. So let's start our today's discussion. So we already cover ninth lectures on this ground improvement, where we am discussing about the introduction of the ground improvement and different other mechanical, chemical techniques. And now we discussing one of the different technique of the ground improvement, which is soil inclusion. That means we apply reinforcement into the ground by improving the ground stability and the strength. So one of these inclusion method is soil nailing. Today we discussing about the soil nailing, and also another inclusion method is encouraging. So first we discussing about the soil nailing. So soil nailing we did or we say we improve the ground, or especially more especially the slopy ground. We improve and stabilize the slope through the soil layering. In soil layering, we inserted the reinforcement and in a borehole, and then grouted surrounded this reinforcement. After a few time, this soil becomes hardened, and the reinforcement will take the all the tension in between this slope. So we minimize, by this way we minimize the slope failure, or we can say in retaining wall also we can use, or we minimize the failure possibility of this slope. So and strengthen the ground. Huh? Huh? Oh, okay, okay. I'm actually I'm discussing the introduction only. So after okay, okay, okay. So let's start our first slide on first slide. So in I think it is okay now. Hello. Okay, okay. So let's start with first slide. So we're discussing here about the basic concept of the soil nailing. So in soil nailing, it is said that the soil nailing is a technique to install the closely paced passive structural inclusion to stabilize the existing unstable ground due to the change of the geotechnical condition by nature and or by human activities. So you can see in this picture that in if you see that in previously the slope is in original slope is in dashes line. After inclusion some or after installing some soil nails in the slope, the the width of the road become increase because the failure possibility of the slope we can minimize and the length of the slope also minimize. So by this way by this way we improve our ground or we increase our slope stability. It is mostly used this technique soil nailing is mostly used for stabilization of the slope. So if you see in the figure, you can see that there is one omega, which is called the angle of the face angle of the soil nailing, and then L is showing the length of the soil nail, S showing the spacing between the soil nails. Then there is uh, uh, and then there is an arrangement about the temporary facing and also permanent facing. And if you see there is shown there existing road and road lining. So in ordinary case we do that in soil lining the existing road if you in original ground condition the existing road width is less. After applying in the soil lining we increase the slope stability of the slope, also increase the width of the road, so by because we minimize the length of the slope. So by this way by this technique we improve our uh, the slope. So in the next slide, here you see that the connection of the soil lining. There is one schematic diagram shown about the connection of the soil lining. So if you see that the arrangement here it is shown that one bearing plate also used, then washers, nails heads, stud heads, reinforcement and all these things are used to act as a nut bolt system or we can say if you apply nut and bolt to join to steel plate like this way we can use this arrangement to uh, include the nails into the soil and to stabilize the ground. So in the coming to the next slide, we discuss about the different types of soil healing. There are many types. So here few are given. First one is grouted nails. So in grouted nails, we use the soil nail to include the reinforcement into the ground. After that, we grouted uh, surrounding the soil nail. Then there is self-drilling nails, then jet grouted nails, and helical nails, driven nails, shooting nails. So most commonly used nails is grouted nails. So now we discuss about the suitability of the soil nail. So in the soil nail is suitable for vertical or near vertical excavation in both soil and weather rock. So this soil nail is mostly used for vertical wall or we can say vertical face of the ground and also near vertical excavation and also it is used for both soil and weather rock. In rock also we can use this soil nail. Then it is also suitable for stabilizing the steep unstable terrain of soil or weather rock. So it is also used to stabilize the steep slope or weather rock, we can say. Then there are favorable geomaterial for. Uh, so now we discuss about the what are the favorable geomaterial which is where the soil name used. So you can see that in uh, it is mostly suitable for steep to hard fine-grained soil. So when the ground condition is soil condition is very steep to hard fine, then this method is mostly suitable. Then it is mostly suitable for dense to mineral soil with apparent cohesion. And then it is also mostly suitable for weather rock with no weak plane. And it's also suitable for glacial soil. Glacial soil in means in the sense it is the mostly available in mountain region where most of the mountain is covered with the ice. And this soil is mostly called the glacial soil. The ground, and also it is used when the ground that can stand unsupported on a vertical or slope cut of 1 to 2 meter for 1 to 2 days. So these are the mostly suitable geomaterial where this soil is used, mostly used. So now we discussing about the where this method is not very much not very much suitable. That means unfavorable geometry. So there are a few ground conditions are given that first one is given that dry, poorly graded questionnaire soil, and then soils with high groundwater table, soil with large boulders and cobbles, soft to very soft fine-grained soil, highly cohesive or corrosive soil, and weather rock with weak plains. So these are the few ground conditions where we cannot use this soil learning technique. So, soil learning technique, when we use soil learning technique, the ground condition should be specific. That means most of the case, there should be some amount of cohesion, or the soil should be stiff to medium, um, stiff to uh, hard clay. Ground water should be like that, or we can say the dense to medium dense soil should be like that. So it is not suitable for the poorly graded soil or cohesionless soil, and also not for when the groundwater table is very high. So these are the conditions we need to check when we apply this soil learning technique. So now we're discussing about the different application of this soil learning technique. So here it is given that the vertical or near vertical excavation, we can use this soil learning. And there is the vertical excavation we done, or near vertical excavation done, to stabilize the side walls of the excavation. We can use this soil learning technique as a temporary basis. Then end slope removal to widening the existing beach embankment. So we use in below the bridge embankment, or we can say at the side of the bridge, to widening the space in between the embankment. So after, if the space it is quite large in between the embankment, there may be possibility there may be less possibility to scouring, and or we can say there is disturbing of the flowing water in abutments. So so this technique is most suitable for this condition in bridge. Then we can also use it is for tunnel portals to stabilize the tunnel in for temporary basis for the construction, and also it is used for repair or stabilization of the existing earth retaining structure, repair and stabilization for existing natural slope. So if we see in these two figure, first one is for soil nail wall for temporary shoring, and a second one is permanent soil nail with highway widening and traffic lane additions. So when we build some retaining wall to stabilize the ground or to carry the slope, before construction of the retaining wall, for temporary basis, we use the soil nail in this ground. After stabilizing this slope for temporary basis, then we safely construct our retaining wall. And then after construction, this nailing temporary railing is removed, and this retaining wall is backfilled with some good soil. So this way, in temporary way, we can use this soiling. If you in first slide also we discussed that in second figure, it is also like that. We use this on permanent basis to widening our existing road. So if we see that in second figure, there is a original slope is in dashes line. So we can remove this original slope by inclusion of soil laning and widening our road, existing road. So which is advantageous in hilly region where the road connectivity due to this widening of road is or we can say suitability is not possible. So we apply this soil laning and existing road can be widened up by this way. So now we discussing about this soil laning which is used in the bridge embankment. If you see that there is one figure is given for existing bridge. So if we in embankment or around surrounding the bridge, if we not apply the soil lane, the existing slope is or original slope is in dashes lines like that. So due to this, the flow in between this below this bridge is obstructed due to this slope, and there may be possibility of scouring, which is dangerous for bridge failure. So to minimize these, we can use or we can reduce the slope by inclusion of this soil nail. And after the inclusion of the soil nail, the existing or we can dashes slope may be removed. So by this way, we increase the space between the embankments, and we can say that the water flow get more easily flow in between this embankment, and then minimize the scarring possibility. So now we discuss the advantages of this technique, or we can say advantages of this soil nail. So first it is said that it is the less right of way requirement than the ground anchor, less concrete use than the conventional reinforced concrete retaining wall. So it is mostly used or mostly advantageous than the ground anchors uh, because of less right of way requirement, and also it is mostly used of or advantageous than the uh, uh, concrete retaining wall, reinforced concrete retaining wall, because it required less amount of concrete than the reinforced concrete retaining wall. Then no need for deep foundation or structural elements below the base excavation. So this uh, in, so when we apply this soil inclusion, so uh, no need there is no need to for the deep foundation. So also it is rapid installation with less material than the ground anchor, and less disruptive to to traffic, and less environmental impact. So this technique when we apply in this slope, so disturbance of induced vibration is very less due to the installation. So it is very environmental friendly, and also uh, when we apply this soil inclusion into the ground, so the movement of the traffic disturbance of this movement of the traffic also become less, then more accessible to a job site, and low overhead requirement due to the use of the light construction equipment. So in this technique we only need some few arrangement only. So first we require some inclusion, that means in reinforcement or rod, and then require some amount of concrete, or we can grout material. By this way only, or some anchor, or sorry, some nut and bolt system. By this way we can uh, in by these few things we can apply this technique into the soil. So it is liquor. So for this it is very accessible for more accessible for every job site or every ground condition region, and also due to the less requirement, overhead cost also become very less, or can say cost of construction or very less. Then higher redundancy because of the larger number of nails than the ground anchor. And so uh, due to it is very suitable, more suitable than the ground anchor, because it is used more number of nails, or we can say more number of reinforcement than the ground anchor. So the higher redundancy, that means the stability also become higher, then more cost effective than the conventional rigid retaining wall. So if you see there in retaining wall, the construction during construction, or we can say before construction, first we stabilize the slope in permanent basis. Then we construct our retaining wall, and it is very heavy or massive structure. So this may be require large amount of money. So by this, if this ground condition is suitable for the soil leaning, then this technique is more or better approach, or more cost effective than the conventional retaining wall, or more we can prefer this soil leaning technique than the conventional retaining wall. Now we discuss about the limitation of this technique. So like other method, there are some limitation. So first one is, this method is not appropriate for the application with strict deformation requirement. So if the ground condition is more more deformable, then this technique is not suitable, because this technique is used only to encounter the tensile strength, or we can say increase the tensile strength of the ground. So there is not designed for the um, there is no, it is not designed for the take care the bending or deformation or shear of the slope. So mostly designed for the take care of the tensile requirement of the ground. So if the ground deformation is more, then this method is not suitable. Then restriction by nearby existing utilities or structure. If there is any underground structure, then a tunnel, or we can say underground utilities like pipes or water line, like that, so then this method is not suitable. Then difficult to install below the groundwater table. If the groundwater table is above the our requirement, or suitable ground above our uh, targeted depth, or we can say, then this method is not suitable uh, because of the existing groundwater table. And then low nails capacity and large keep deformation in high plastic cohesive soil. So already we discussed that the method, if the ground condition is very deformable in nature, or we can say there is a possibility of large keep deformation in longer period, then this method is not suitable. Now we discussing about the different failure modes of this soil leaning. So the failure mode is divided in three ways. First one is internal failure, then second one is external failure, and third one is phase failure, like that way. So we first discuss about the internal failure. So there are four way to fail internally this soil nail. The first one is nail soil pull-out failure. So in nail soil pull-out failure, the soil nail, including the grouting, is pull out from the ground due to the heavy weight of the or movement of the slope. So then, and this failure is occur. Then bar grout pull-out failure. So in this failure, the bar which is included into the grouted material, is coming out due to the force which lateral force which is coming from the slope. So due to this bar is failed because it is pull out from the grout. So this is called the bar grout pull out failure. Then nail tensile failure. That means if there is lateral force is more, when side lateral force is more, there may be possibility that the bar the tensile stress of the bar is exceeded is ultimate strength. Due to this, there may be breakdown or breakage into the bar, and this is called the Nils tensile failure. Um, and the last one is in internal failure is nail bending or shear failure. So due to the ground deformation, or we can say that in the we say that is that in dashes line there the ground is uh, is collapsed, and due to this there may be possibility of the bending and shear failure of the soil line. Now we sorry for that. Okay. Now we hello. Now we discuss about the external failure of the soil line. So yes. Now we discuss about the external failure of the soil nail. So there it is divided in three ways. First one is compound failure, second one is sliding failure, and third one is global failure. This failure is mostly similar to this failure of the retaining wall. So like that way also this failure is discussed. So first one is compound failure. So when there is a critical surface is it is joining um from the toe of the wall to the surface of the ground, and this like failure when there is soil strength is less than or we can say soil less, there may possibility of the this type of failure. This is called compound failure. Uh, Compound failure. Then there is sliding failure. That means if there is huge lateral force is coming from the slope, the oil maybe moves in sideway. So then this failure is called sliding failure when the soil strength at the base is less than our requirement. Then uh, global failure. Global failure means which is similar to the base failure. That means all the all of the our arrangement is failed due to the less strength at the base of the we can say base of the slope. So this type of failure is happen. Now we discuss about the soil nail. There are three types of phase failure is occur in soil nail. First one is facing flexure failure. In facing flexure failure, the wall or of the temporary wall or permanent wall of this soil nail may bend due to the plastic movement of the ground, and this face flexure failure is occur. And then there is facing punching shear failure. In facing punching shear failure, the soil, the nail is punch into the uh, punch into the ground. So with its arrangement. So uh, so uh, it is occur when the force apply during the tightening of this nut and bolt is more than the requirement, then this type of failure is occur. Then the last one is headed start failure. Headed start failure, we can say joint failure, or most of the time we can say this joint failure. That means the joining of this inclusion, we can say bar, into this wall is failed by due to some less uh, strength of this nut and bolt. So by this way, this type of failure is occur, and this is all. This is three are called phase failure. Now we discuss about the load and deformation transfer during the construction. So how this this load is transferred to the soil due to the deformation and load transfer during this construction. Now we discuss one by one. So if you say, uh, or we can say, if you see this figure is in there, there is arrangement of the soil nail in different phases. Nail one, nail two, and like that, nail n. So in when we apply nail one into the ground, there is possibility of the deformation of the soil. Uh, there may be possibility of the. Please wait few minutes. I will come. Please wait. Sorry for that. There is some technical issue. So now again we start from here. Okay. So we're discussing about the deformation and load transformation mechanism of the soil nail. So if you see that there is different way or step by step this soil nail is included or uh, inserted into the ground. So then there is n number, we can say there is n number of soil nails. So first soil nail is inserted and the deformation and failure mode of the soil is given here. If you see that the wall is deformed is one, two, and like that way this wall is deformed. So and there if you see the one chart is given based on the existing force versus the distance from the wall. So in when we apply the soil nail into the ground, the face at the face there always some amount of force is there. So after that, if we increase the distance, the force is increasing. Axial force is increasing. After after at a certain point, this force is maximum. After that, the force is reducing with increasing the distance. Like this way, every soil name is face this axial force. So if you see that here also the possibility pattern of the deflection also given. You can see in the left corner deflection pattern at the end of the each face also given like this way. So n nil, when we apply nil number n, the possibility of deformation of the wall is we can see in the figure like that way. Also 2 1 also like that. And also there is failure surface also. So for nail 1 also drawn, nail 2 also drawn, like that nail n also drawn. And this is called critical failure surface for excavation phases, for every excavation phases. So, and this critical surface is mostly find out about the maximum, where the maximum axial force is maximum, where the axial force is maximum. And like this way, we find out this critical surface. And now in very precise way, we can also discuss this load transformation. If you see that in above or near the ground, the axial force requirement of axial force is more than the at the at the below of the, or we can say near the toe. So if you see that the zone, there is two zone is given here. One is active zone and another one is resistive zone. The active zone is, we can say, the failure zone, where the soil is failed due to some external forces or some loose or compacted fail. The slope is fail in active zone, and there is one portion, another portion of the slope which is resisted this active zone. And when we inserted the nail into the ground, there is shear force is developed due to the movement of this nail. So if you see that the direction of the shear force in active zone towards the wall face or towards the nail face. Uh, but in resistance zone, it is opposite. That means outwards the uh, wall face. So, and you also see that there is one point where this axial force is maximum, and this, if we joining this maximum axial force line point, we can find out the critical failure surface for every uh, for this soil name, or for this arrangement, critical failure surface. If you joining this every point of this maximum axial force, again there is given the shown the maximum tensile force, location of the maximum tensile force, and also the critical failure surface. So you see that there is three arrangement is given based on the different depth. So the in figure it is said that the occurring of the maximum axial force is in between the point 0.32 to point 0.4 h. H is the height of the facing or height of the wall, you can say. So, and if you joining this every point in this every or depth where the the axial force is maximum, then we can get the critical failure surface. Is critical failure surface. So during our construction, uh, in every construction we can say we maintain some factor of safety for to minimize the extra possibility of the ground or a failure possibility of the ground. So here, if we apply the factor of safety to this to this existing local maximum soil name, so then we can get another critical failure surface for limit equilibrium with factor of safety is FSQ, and we see that the there is shown that LP is nothing but the length of the uh, soil nail in resisting zone. This is called LP, and and if you see that there is some dashed line in the graph in, or we can say LP, the the load deformation is dashed. That means this dashed line is used. That means this area is most important to resist the soil nail, and most of the our designing of the soil nail is for this resistance zone only, because this active zone is already filled. There is no need for this designing of the nail for this active zone. So we need to design for the resistance zone, because the if there is if soil resists the nail, then only the wall is stay, or we can stable for this slope. So now we discuss about the different pressure distribution for different arrangement. So here it is given the pressure distribution for different arrangement. First one is given for the mechanically stabilized wall. And second one is given for the soil nailed wall, and third one is given for the anchorage wall. So we can, if in stabilized wall, mechanically stabilized wall, the earth pressure distribution is like that. At top it is zero, and at bottom there is some pressure due to some height of the wall. But it is opposite for the this earth pressure distribution is opposite for the soil nail wall. At top it is maximum, at bottom it is almost zero. And in anchorage wall, the at top it is similar to the mechanically stabilized wall also at top, but at top it is zero, but at after few distance the earth pressure distribution is constant. There is so these are the three diagrams where we by this we can see that the distribution of the earth pressure for different arrangement. Now we discuss the simplified distribution of tensile force uh, in soil nail. So what are the different forces is applied at a different zone in the soil nail? We can now discuss. So in first, at near the face there is uh, you can see that at the face uh, at the face of the soil nail, or at the face of the wall, there are some minimum amount of T naught amount of we can say amount of force always is there, and this force is nothing but the connection in between the soil nail and the face. So there's some amount of face strength is there, and after that this face strength is increasing with the distance due to the soil nail arrangement, and after at a particular distance the this existing or this axial force or tensile force is maximum, and further this force is after further increasing the distance, this force is reducing. Force is reducing, and so at a LP distance from this maximum point, that means this force is become zero. So the zone is divided. This force distribution is divided in three zones. So at near the face, the force is called facing capacity (RF), is denoted by the RF, and near the maximum tensile force, this is called the RT, which is called RT. It is nail tensile capacity force, and after the maximum tensile force, the zone is called pull out capacity zone. So here three possibility or three condition is given for the three different failure. One is first one is for pull out control. So in pull out control, the RP is less than RT from everyone, from every possibility. That means RP is less than RT, further less than the RF. Then only pull out failure is occur. And tensile failure occur when the RT is less than and the RP less than RF. And then phase failure occur when the RF is less than RP, or RT RF is less than RT. And this is controlled by the T naught by T max. T naught is the phase strength, tensile strength, and T max is the maximum tensile strength during this soil needling. And this and the maximum is dependent on the ultimate strength of this soil net. So we define this ultimate strength by Tu, which is equal to pi into d suffix dh into tau u, where tau u is the ultimate load transfer rate, and dh is the uh, uh, dia of the dia of the borehole, where we apply or inserted this nail. So by this figure, we can easily identify that, find out the different possibility of the different failure mode of the soil nail, and which one is governing in our designing. Or if we say pull out, the govern in pull out failure, the governing is RP. The governing force is RP, and in tensile failure, the governing force is RT, and in phase failure, the governing forces is RF. And each and every case, these forces is minimum. Now we discuss about the maximum tensile force in surveys. So, and this to find out this maximum tensile force during our service condition, one chart is given, and by this chart we can easily find out. And this chart is in between the depth of the nail height and the normalized maximum nail load, and it is normalized by T, that means tensile force, by Ka H gamma SHHB, where K is the active earth pressure coefficient, H is the height of the wall, gamma is the unit weight of the soil, and SHHB is the pacing in horizontal and vertical direction. So if you see that the due to uh, uh, increase the depth, after a particular point, the tensile for maximum tensile force nail head load or normal nail head load is reducing up to h is equal to small h is equal to two third of the h. The nail normalized coefficient is 0.75. After further increasing the depth, that means from two third h to full capital H, the normalized coefficient is zero point 0.5 and is reducing and become zero point 0.5 at h. So, and this by this diagram we can find out the maximum payload during our service period with different depth. Oh, sorry. Okay. Now we discussing about the different design consideration. So before discussing this, I think we can here we can give 5 minutes break here or take 5 minutes break here. After that, we can join again. So please wait, don't leave. I will join after 5 minutes. Sorry for that. I'll join again. So welcome to this lectures. Again, I am now again sharing my slide. So we already discussing about the sorry approximation of the maximum is service tensile force. Now we're discussing about the consideration. What are the different consideration cons or assumption we take during our designing of the soil nail. The first one is given that each nail has a influence area less than equal to 4 meters square. That means the if one nail is included into the ground, the coverage area or the surrounding area, improved area should be less than 4 meters square. The nail spacing should be 4 meters. The minimum length of the lane nail is equal to zero point 0.5 into h. H is the height of the wall. Drill hole diameter of for grouted nail is 1000 to 200 mm. For gravity grouting and efficient nail tensile capacity, nail inclination should be 15 degree. Recommended minimum stability for different failure modes under static loading are provided in table. So you see that there is different sector 50 failure mode is given. Here, this sector 50 is divided in two failure modes. One is external and another one is internal. And based on this factor 50 is given. For in external stabilization failure mode, the for going in long term member structure, the factor safety is 1.35. For permanent stabilization, the factor of safety stabilization is 1.5. And for short term, this factor of safety it is in between 1.2 to 1.3, and for permanent structure it is uh, 1.5 to 1.6. For sliding, for temporary it is 1.3, and for permanent it is 1.5. For bearing capacity it is for for temporary it is 1.3. Now it is in permanent nail, this factor safety is 2 for temporary and also for 2 for permanent structure. For sliding or tensile failure, nail tensile failure, the factor safety for both temporary and permanent structure. Now, capacity, different capacity used for the designing of the soil nail. First one is ultimate pull-out capacity. It is given by the R is equal to the T naught pi into tau d subscript into where T naught is the capacity between the nail and facing wall. The ultimate bond strength of the nail and soil or rock. H is the average drill diameter of the drill hole is equal to the Q. And then the rear pull-out is denoted as that means pull-out strength is the pi tau LP, where LP in the resistance zone, length of the soil nail with resistance zone. So by these two formula, we can find out the ultimate pull-out capacity, also capacity. Now, to find out the capacity, we used or we can some different charts based on the nail force to find out the nail force and length. And to use these charts, required, we can say there are some specification is required before the chart is created. So ground condition should be homogeneous. Nail inclination angle is equal to below the horizontal direction. Safety SST is equal to 1.35 for minimum length and for SST is equal to 1.35. Then nail diameter T suffix DH is equal to 100 mm. Normalized cohesion is 0.02, and this normalized cohesion is C by soil, gamma is the soil, and H is the height. Now we can say this is yes, normalized coefficient. So now to use this chart, so normalize coefficient is given by this mean normalized bond strength is given by tau u into ds divided by FPO gamma h, where tau is the ultimate bond strength, ds is the factor of safety, gamma is the unit, and SHSV is the facing for horizontal and vertical. And then we to find out after that we find out the normalized maximum design nail force, and then we find out the maximum design nail force. So T suffix max S is the maximum design nail force, and it is find out the normalized design nail force into gamma H into SHSV. And then after that, sorry, again, so after that finding out, we applied some correction because uh, we those value for length, finding out the length and maximum force, it is only for some few assumptions. That means nail diameter, sorry, borehole diameter is 150, face angle is 15 degree, and like that way. So, and also C star, the normalized cohesion is 0.02. So like that. So if we apply for different values for bore diameter and for different length, we use some correction. And for finding out the length of the soil nail, we use L by H corrected is equal to the C1 L, C2 L, C3 L into L by H, which chart, which is get from that. Find out for the normalized design nail force corrected. We apply the C1F into C2F into maximum nail force. So this C1L, C2L, C3F, and C1F, C2F is the correction factor. It is find out based on the different formula, empirical formula, and so here it is given that table is given the roof material, and this table is for the finding out the ultimate bond strength of this soil nail. So we use rock material, and the construction method is rotary drill. Then types of rock. These bond strength range, like example, for marble, the ultimate bond strength is in between 300 to 400 kPa. For chalk, it is in between 500 to 600 kPa. Like this, we can find out this ultimate bond strength. Now, if the we apply or we can say the material is question is soil, and we apply the construction method for this question soil, and for different type of soil, the ultimate bond strength also differs. So for rotary drill in question soil, if you apply for construction method is apply rotary drill. For sand, the length of this nail is in between 100 to 180 kPa. And for transparent soil, we find out and also it is given for the cohesive soil also, saline soil also. So and for it is also given for different construction method and different soil. For rotary drill in siltic clay, the ultimate warmth of the soil nail is in between 35 to 50 kPa. So these are three charts we use to finding out the bond strength of this or uh, of the soil nail, and by this way we choose our nail property. So now we discuss about the application of these charts, which is given to find out the length and tensile maximum force, axial force, or design nail force for our soil nail design. So there is four possibility is given or four condition is given when the face angle and also the back slope is 0, and one is given when the face angle is 15 degree or 10 degree, back slope is 0, or we can say second one is given for when the face angle is 0, back slope is 10 degree. Next one is given for when the face angle is 10 degree, back slope is 0 degree, and then last one is when the face angle and back slope both are 10 degree. So four charts by this way, four charts is given. So after so to use this chart, first we have to normalize bond strength by mu suffix p naught formula. So by this mu suffix p naught formula, it is tau a into dh divided by fs into gamma into shhb. By this formula, we find out the mu, where tau a is equal to tau u into fs p naught. That means allowable bond strength. Tau is allowable bond strength. After finding this TA from this chart for different angles, that means 27 degree, 37 degree, 35 degree, or 39 degree, we find out the LH, L by H, and tau, TS, that means normalize maximum nail force from this chart. So above one is for, if you can see this chart, there's two line is drawn. At one is below, another one is above, on the upper side. So the upper side is for the L by H, for the L by H or different and uh, 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 and below one is for finding out the T normalized nail force. And then if we multiply in this normalized nail force into with the gamma h into sh into hb, we find out the total or maximum normalized nail force. So after finding that, and one chart is given for this correction C1L or and C1F, which is for the drill hole correction. And if we say in our charts, which is given for 100 uh, if we bore diameter, but if we apply this chart for you can say for different by this chart read out the correction factor. The dashed line for C1 so let's C1 chart only for correction. We discuss another important technique which is related to the planning and it is so one for schematic which is given for the different ground implement technique which is similar to this soil nailing. So the first is which is when one nail is inserted, we can say one rod is tendon is inserted and at the end of the tendon routing is applied. And then second one is for the soil nailing, which is already we discussed now. And third one is for micropiles. By this way, micropiles we stabilize the ground. And the last one is for the slope stabilizing piles, which is mostly inserted at the toe of the ground to minimize the potential failure of the slope. Now we discuss about the soil anchor, which is most commonly similar to the soil nailing. A similar way is soil nailing is used. So it is said that the ground anchors are cement grouted pre-stressed tendons installed in situ in soil or rock by transmitting applied tensile load into ground to stabilize the earth retaining structure or to provide a uplift resistance to the so this is the cement grouted which is similar to the soil nailing but it is pre-stressed tendon but here it is pre-stressed tendon installed like pre-stressed concrete uh, some where some previously stressed uh, tendons are inserted then apply concreting and like this way also some pre-stressed which is already stressed in compression or like that or we apply here and then at the end we use the cement grouting which is useful mostly useful to take the tensile load from the ground and stabilize the earth or and or we can say and also sometimes used for the structure from the upliftment of the structure. So this anchorage is consist the anchorage set which is consist of an anchorage head, a bearing plate, and a thumb pad. Then unbonded pre-stressing steel tendon is used. Then it is consist of bonded steel tendon with grout. Now there is some points are given. So first is to transmit the pre-stressing force from the piston to the ground surface or the surrounding soil. So this anchorage arrangement it is from the uh, stress from the ground from the uh, piston stress from the steel to the ground surface or the surrounding soil. The unbonded steel is pre-stressed and can be or can have tension and transfer the resistance from the bond length to a structure. Uh, the bond steel with grout can be provide a tensile load into the ground. Therefore, the bond length should be behind a critical slip surface. So it is made in like a way that the unbonded and bonded steel. And unbonded steel is directly inserted into the ground, and bonded steel is inserted with the grouting material. In unbonded steel is face the elastic elongation and transfers the resistance of the uh, resist or transfer the or we can say resist the ground. But in bonded steel, which is applied with the ground, it is provide the tensile load into the ground, and there it is mostly used uh, above the or we can say at the behind the failure surface. That means behind the failure surface, mostly resistance zone it is applied. So there is one arrangement is given anchorage, ground anchorage arrangement is given. You see that it is used at the top of the anchorage. There is one is used uh, to insert it or clip this anchor into the ground. So this arrangement are consist of anchorage set, anchorage head, bearing plate, and wall. By this way, this anchorage is put or inserted into the ground, and then this anchorage is divided into two zones. One is unbonded length, another one is bonded length or anchorage bonded length. In unbonded length, there is use centralizer, and in bonded we use grout like that way. And this bondage length is used behind the critical slip surface. That means behind the failure surface, this bondage length is used. So now uh, there is type four way. There are four way we use this anchorage into the ground. First one is straight shaft gravity ground anchor. Then we have pressure grouted ground anchor. We also use post grouted ground anchor, and then under rimmed anchor also used. There four figure are given for grouting material for different anchorage. So type A, first one is for gravity shaft gravity ground or shaft gravity ground. So simple, we inserted the tendons into the ground, and then after that we apply at the behind the critical slip surface. We apply the grouting material. Second one is pressure ground. In stiff sharp pressure ground, we, hello, please muted your mic. Uh, okay. So at type B, we if you see in figure, it, so the difference is that the grouting. we apply it is a pressurized grout. That means by pressure we apply this grout, and due to this the diameter of this grout is increased. Then post grouted in the sense after inclusion of the anchorage, uh, uh, we uh, we use after the grouting material. So like that way we use and then under rim. Like under rim we use under rim price under rim price there is some bulge uh, arrangement is there which is used to resist the uplift pressure. So like this way also we use this anchorage in the like under rim some bulging of this or you can say stepping method is given which is resist the uplift force. Now discuss the installation drilling. So first we can drill the ground. We insert a steel tendon within the bond length and install the anchorage and pre-stress the steel tendon. So this is mostly used drilling technique. So after drilling, we insert the steel tendon, but the grouting is given at the bond length. That means at the behind the critical surface or critical failure surface. And then we uh, install the anchorage assembly, like we apply the nut and bolt at the face of the wall to stabilize or to make it stable at the ground. And then we apply the pre-stress at the steel tendon, like similar to the pre-stressed concrete. So you use. Now we discuss about the suitability of this anchorage method. So these ground anchorage are suitable for a variety of technical conditions. They can be used in situ soil, rock, or other geomaterials. Different techniques may be used to use this ground anchor in different geometries, mostly related to the drilling, steel hole. Ground anchor may experience excessive cliff deformation when they are installed in organic or high plastic soil. Hence, caution be exercised when the ground anchors are installed under such a. So it is said that these ground anchors mostly used for different types of soil, like soil rock materials or different geometry, and also used for take care of the cliff deformation. I mean installation in high organic and uh, there's precaution should be given due to this cliff deformation. And this technique is used for different then there is discussion here it is application where it is mostly used. So the ground anchors have used permanently or temporarily. Permanent ground anchors are typically designed for the service life of 75 to 100 years. That means if we used or we can build this ground anchor in permanent way, then it is 75 to 10 years period. And for temporary anchor are mostly used for the earth support before permanent structure are built. Earth support means it is mostly used for when we apply it is mostly used for the excavation purpose to stabilize the side walls to hello mm, also used for the mm, uh, stabilize the base of the foundation due to upliftment. The ground anchors are commonly used for lateral earth support during the excavation, stabilizing the unstable surface, and uplift resistant to foundation below a groundwater table. So this soil nail and also ground anchor is mostly used for lateral to stabilize the lateral slope and also to stabilize the unstable slope. This grounding force is advantageous than the soil nail because the soil nail is not used below the ground table, but this anchorage is mostly used below the ground table to resist the upliftment force during the foundation. Then we discuss the different application of the ground anchor by some schematic diagram. So first one is for the retaining wall. So in retaining wall, we apply to stabilize this wall. We also apply this ground anchor. So you can see that this anchorage is unbounded length, and bond length is below behind this critical surface. So like this way we can use. We can also use for slope stabilization. So in stabilizing the slope, we can use this, and then also use for to resist the upliftment force or uplift force during the construction of the foundation at the base of the foundation. So if you see that if the groundwater table is very high or close to the ground surface during the excavation, there may be a risk of the upliftment of the base of the floor due to the seepage force. So to resist the seepage at the base and to stabilize this, and the last one is for dam stabilization. So to minimize the seepage, to stop the seepage, we apply this anchorage at vertically at the face of the foundation, and due to this, seepage or maybe at the below the concrete dam should be minimized, and due to this, we can reduce the uplift force of the concrete dam. Now we discuss the advantages. What are the different advantages of this ground anchor? So here it is said that no obstruction for workspace during excavation, tolerable to large earth pressure without a significant increase of wall cross section, used as temporary excavation support as well as permanent structure. No need to select backfill, no need to deep foundation support, fast construction, and less surface right of way issue. So it is most of the case it is similar to the disadvantage is similar to the soil nail. So same, this is when we apply this retaining wall, there is no need to backfill it. There is no need to any deep foundation to support this anchorage, and no obstruction also required during this workspace. That means if you apply this technique at a slope, stabilize the slope near the existing road, there is no need to disturb this traffic in this road. We can use easily without less arrangement, with less arrangement, very fast construction very fast to now limitation. So in limitation, it is said that the ground anchors may be limited by objects in the ground and ground right of way surface. So they may not work well in soft soil due to large cliff deformation, and difficulties may be arise in constructing watertight connection at the anchor structural slab interface below the groundwater table. which is occurred during the installation, the ground anchor. So for this we cannot use for this we cannot use this ground anchor. Now we see about the load transformation behavior. Uh, so if you remember in soil learning we're discussing the load transformation which is throughout the soil learning. The load transformation is occur is throughout the soil learning. But in load transformation is occur at the bondage length only because soil is it is installed behind the failure surface. Above the failure surface, there is no need to install. There is no possibility of the occurring of any force. Only there is only there is only tension is happening through the tendon. But in bond length, which is behind this critical surface, we can see that the bond shear stress versus bond length curve. So here we can see that at the critical failure surface, there is some minimum bond stress is happening. After increasing the distance, the strength is also increasing, and this is due to the friction, or we can say grout material and the surrounding area. So like this way, this load is transferred to the soil during this ground anchor. And now we discuss the different failure mode. So there is also some this ground anchor also filled by different way similar to the soil name. So it is or first one is tensile failure of tendons. So to the soil nail, it is failed by tension after if the tensile strength, ultimate tensile strength is due to we can say the strength of the tendon is more than the ultimate tensile strength due to the lateral movement of the wall, then this may be failed. This is one type of failure. Then pull out failure of grout or grouted bond. So if this grouted arrangement is removed, or we can say uh, it is pull out from this arrangement due to lateral force, then this type of failure occur. Then pull out bond. So this is similar to the pull out in pull out failure. There is arrangement with the tendon also, grout and tendon also pull out from the wall. But in pull out failure of tendon, only the tendon is pull out from the grouting material. Then this type of failure will occur. Then failure of grouted bond. Due to the creep deformation or due to the plasticity of the soil, there may be a possibility to the fail the face of the wall, and due to this there may be bending and shear may be due to this the strength of the or the arrangement of the ground anchor is failed, and this is called the failure of wall in bending. Then failure of wall due to the insufficient passive capacity. So we know that when we constructed some retaining wall, there are three types of pressure is created. One is active pressure, another is passive pressure, and then pressure at rest. So if we arrange or we constructed our wall, if it is balanced by both pressure, okay, active and passive pressure. So if our passive pressure is equal to our active pressure, which is generated behind the wall, then the wall is moved forward, and due to this, sometimes the ground may fail, and this is called to insufficient passive capacity. Now there's uh, 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 again there are different failure modes also. So it is said there, first one is failure by forward rotation. So F is said failure by forward rotation. That means the wall face of the wall is rotate, and due to this wall is fail. Then failure due to insufficient axial capacity. So due to uh, axial capacity of the wall, the wall is inserted into the ground, and due to this the wall may be failed. And failure by overturning due to the whole arrangement is overturned due to we know this overturn is happening when the existing force resisting force is less than the overturning force. Then only or we can say yes, overturning force. Then this failure occur. Then failure by sliding due to the force. If the resisting force is less than the lateral force, then sliding failure occur. Then rotational failure of ground mass, and it is occur when the base failure uh, is occur when the whole the soil pushed into the field, and uh, that means whole ground is failed, and then this type of failure is occur. Now we discussing about anchor wall, and this is based on the active, passive, and stable zone, and potential failure surface, bond and unbonded line. And this occur during our construction of the anchor. For internal stability of an anchor, one arrangement is given, and in arrangement we can see that above the critical zone, the zone is called the active zone. Or we can say at below the zone is called passive zone. Uh, at the toe, at the right side of the wall, the zone is called passive zone, and then above the failure surface, the zone is called potential failure surface, failure surface, and below the surface, the zone is called stable zone. And the angle between the potential failure surface and the failure toe resistance is uh, and the depth of the wall in passive zone is D here, and the depth of the wall above the passive zone is given H up to the ground surface. And these are the arrangement is required to find out the internal stability of the wall. So internal stability of the anchor wall, in a typical anchor wall, there there are active, passive, and stable zone. Here we can see that the active zone is right behind the wall facing, but in front of the stable zone. The passive zone is right in front of the embedded wall facing. The active zone and stable zone are divided by the critical failure surface. The unbound length of the anchor is mostly located within the active zone. The entire bond length is mostly within the stable zone to provide the tensile resistance to the active zone. Passive zone provides the total force of the to the wall when there is a sufficient toe resistance. The potential failure surface is occur, from the base of the excavation. So these are the points we need to remember during the construction of the or find out the internal stability of the anchor wall. And these are the arrangement also we given. Now we discuss the lateral earth pressure of this anchorage wall, and it is different from the lateral pressure of the retaining wall. And it is found out by Tarjagi and Peck, and it is developed the lateral earth pressure diagram based on the back calculation of the field measurement, the start load, and the internally braced excavation with with the following assumption. And assumptions are large excavation with an excavation depth greater than 6 meter, large wall movement or to fully mobilize soil shear strength. Ground outer table is below the base of the excavation. Homogeneous soil under a drain condition and undrained condition for clay. Load diagram corresponding to the wall portion of the base of the excavation. And these are the assumptions. And by this way, we find out this lateral earth pressure of this anchorage wall through back calculation. And here is given for different earth pressure, lateral earth pressure diagram for different type of geometry. First one is given for this sand, second one is for stiff hard fissure clay, and third one is for soft to medium clay. So the maximum the intensity of this uh, pressure diagram for sand is given is here is 0.65 K into gamma H, where K is the lateral earth pressure and gamma is the unit on which K is defined is here is 10 square into 45 minus 5 by 2, where 5 is the internal stability of the soil. And then second one is for stiff hard fissure clay, and it is here the pressure distribution is typical trapezoidal, and the maximum pressure intensity is zero point 0.2 gamma h to zero point 0.4 gamma h, and it is mostly in between middle portion and zero point 0.5 h length. And then the last one is for soft to medium clay, and it is first it is 0 at the top, and after a 0.25 h this is intensity is constant, uh, and this intensity is equal to that k gamma h 1 into k gamma h, where k is 1 minus is a constant which is given by 1 minus mba 4 cu by gamma h. So by this way we find out the pressure distribution in the soil. So here also one typical design diagram is given, and it is already similar to the first one we already discussed that. And again it is very precisely shown here. Unbounded length, what are the minimum length of the unbounded length? Here it is given 0.45 meter, and the failure surface is 3 plus 5 by 2, and the bond length and there in between unbound length and bond length there are some gap is given, and it is given by x, which is greater of 1.5 meter or h by 5, whichever is greater, and the minimum depth of this unbound length it should be point cover from the ground surface it should be 4.5 meter. And also there is shown the different zone, stable zone, active zone, like that way, different way we design our anchorage. Now uh, these are the some few points based on this diagram uh, and already discussed earlier, and we skip it because these are not shown in the this diagram, and it is already show. So now we directly move on to the problem. Due to the less time, we move on to the problem which is discussed here. So, now we discuss the problem which is discussed in this uh, soil nail. The problem which is based on your assignment and purpose is your ground purpose. So it is for solving the soil nail, and for this we need charts, and to find out this we need charts. So it is said that the problem is said that for excavation in a silty sand, a permanent soil nail wall was proposed. The depth of excavation is 8.5 meter, and the wall is vertical, and slope of the top surface is 10 degree. Cohesion, friction angle, and unit weight of the stiff sand are respectively 4 kPa, 30 degree, and 18 kilonewton per meter cube. The the required global sector of safety is 1.5, and factor of safety against pull out is 2. Design the soil nail, spacing, length, and size of the nails. So we need to design this problem. So the ground condition is given here that the top soil surface is 10 degree. Slope of the top soil surface is 10 degree. So to find out the this design to design this, we need to first we go to the charts, and if you remember that we discussed the set of charts. If we I'm quickly go back to these slides. If we wait, yeah, yes, there is, and there are four type of charts is given. So for our ground condition, it is given that the back slope is 10 degree. So you can see there this type of arrangement is given here. If you see, I am zooming in. If you see that this type of arrangement in our problem is given here. So we need to first find out the normalized bond strength by some this formula. Above you can say mu p naught. First we find out the normalized bond strength. Then after finding out the normalized bond strength, we from this chart for 30-degree angle, we find out the normalize design nail force, also find out the L by H coefficient. So after finding that, we putting this coefficient into these formulas, we find out the maximum design nail force, also find out the length of the nail for this arrangement, and then we apply the correction factor for our requirement. So now go back to this formula problem again. So you see that here it is. This problem also, this chart also given here. So now based on our ground requirement, here it is given the silty sand. So based on the ground requirement, first we find out the total ultimate tensile strength from this chart. So for silty sand, it is given that 100 to 150 kPa. So if you average it, then it is come about 125 kPa. Now we find out one by one this. So now first we assume that the diameter of the drill hole is equal to 150 mm, and assume also the inclination of the wall is about 15 degree. The ultimate bond strength from this chart is find out about 125 kPa. which is average in between the 100 and 150. Then we also assume the horizontal passing spacing is 1.5 meter. After all this value put into this formula, that is mu p, mu suffix p naught is equal to tau u into d uh, suffix dh divided by fs p naught gamma sh sb. We find out about the coefficient is 0.231, and also find out the normalized coefficient by c by gamma h, and we find out the normalized coefficient about 0.026. So from charts for mu p naught uh, 2.31 and phi is equal to 30 degree and omega is equal to 0 degree and beta is equal to 10 degree, we find out that L by H is equal to zero point 0.7 from chart and T max S is equal to 0.25. After that, we apply the corrections for our requirement. So we use the borehole diameter is 150 mm, but this chart is given for the 100 mm, so we need to correct it. And for there is different corrections: C1L, C2L, C3L for length correction, and C2F, C2L, C1F for force correction or tensile for maximum axial force correction. So by this empirical formula, so for drill hole correction, that is C1L and C1F, we use the chart. But for finding out the correction for C2L or C3L, these few empirical formula is given. For C2L, it is given by minus 4 C star plus 1.09, and for C3L and also C3L, it is given which is called for factor of safety correction. It is given by 0.52 factor of safety plus 0.35, because in our original formula the factor of safety is for 1 point, so the chart is designed for 1.35, but here it is given different type of factor of safety. Also this chart is given for the normalized equation 0.02, but we find out that our normalized equation is 0.02, so we need to correct it. After applying the correction, value for H is given here 0.5775, and this should be the value. And after applying this formula multiplying with the height of the wall, we find out the length of the nail is 5 meters. And like this way, sorry, like this way, we also corrected the uh, normalized nail force. And after that, this coefficient is about 0.36. No, and this coefficient, when we put this coefficient into the formula, that is T max, small t max S into H into gamma into SHHB, we find out the total maximum nail force, that is 126.5, and then we find out the maximum design nail force at the nail head. For this, we use uh, one formula: T T naught is equal to T max into 0.72 into S max is maximum pacing in vertical and in uh, horizontal direction. So after all this put into this formula, we find out the total maximum nail force at the head. And now these are the now we discuss this. Now one here is one deep excavation given here, which is used, uh, which is not required for your exam purpose. So now we close here. It is already 8:06, and about mostly specifically discussing the soil nail and also problem one problem. And up to this I think uh, uh, all the portion of this soil nailing and encouraging is covered, and it is this problem is very important for your uh, exam purpose. So now we close our session here. It is already 8 p.m. So thank you everyone. We will meet again in next week, which is week 11, and only 2 weeks are left. And if anything left, I can cover this one extra week. So don't worry about this. And also these lectures are uploaded to my YouTube channel, and also I am sharing this material to Google Drive. So don't worry. So thank you for this session.